So I should point out again, my lecture notes are again updated on my website. They should be complete for this lecture, and I already have some material for the next lecture, but I might update that before tomorrow. So we've come to the time in the week where somebody has to say what a perfectoid ring is and what a perfectoid space is, so that we can start talking about examples in the other series. So my plan for today is to do that. This will be a pretty efficient trip through this subject, which is to say I won't give too many details of basic steps. My hope is that since we went through the case of perfectoid fields in some degree of detail, I can say some things that look plausible by analogy and maybe make some comments about to what extent the analogy essentially works without too much change, and to what extent really some extra arguments might be needed. But I do have an important chunk of material I need to get through, so I'll try to make sure that I keep on track and do that. Okay, so one thing I should warn you about is that there are different levels of generality in which one can present this theory. So I'm going to strike a middle ground between some of the references. So convention. So I'll make this a convention about Huber rings, and then it will also imply a convention about perfectoid rings. So we've talked about Huber rings and pairs in the lectures on adic spaces, so I'll refer to those notions. But in my lecture, I'll be a little more restrictive about Huber rings A and Huber pairs. So in particular, I will assume that A is always separated and complete for its topology. So in the presentations on adic spaces, this wasn't assumed initially, but when you define the structure pre-sheaf, all the rings that you see actually are separated and complete. So it'll be easier for me to just start with that hypothesis built in. And I will also assume what was called the Tate condition yesterday, which is that A contains a topologically nilpotent unit. And I will sometimes want to refer to a particular one. I mean, the particular one is not going to be in the data, but I do sometimes need to refer to one. So I'll use this letter var pi for this. And the phrase topologically nilpotent unit is a mouthful, so I'll replace it with another mouthful. It's often, such a thing is also called a pseudo-uniformizer. Why is that? Why is it called that? Well, the example, I want to include the examples of non-Archimedean fields, right? Non-Archimedean fields should be Huber rings. They're separated and complete, and because I insist that the absolute value on a non-Archimedean field is not the trivial absolute value, there is some element which is non-zero and has absolute value less than 1. And so any such thing would be a pseudo-uniformizer. In a non-Archimedean field, you may take any element or pi whose norm is not 0 but is less than 1. Right? So if somehow I were talking about a discretely valued field, I could take an actual uniformizer and that would have this property. But in general, I will be talking about things like perfectoid fields, which do not have uniformizers. So an element like that is referred to as a pseudo-uniformizer because it does it is topologically nilpotent, so you can view the ideal of definition in the valuation ring as being the principal ideal generated by this element, but it's not a distinguished choice or anything. So I'll make a comment. This also came up yesterday. This can be relaxed slightly. So a slightly weaker condition that would also work for most of the theory is the condition that the Huber ring is analytic, which means that the topologically nilpotent elements generate the unit ideal. So of course, if one of them is a unit, that's certainly true, but it is possible, but not entirely easy, to make examples that have this weaker property but do not have a topologically nilpotent unit. So the difference between these two is essentially that when you start globalizing, when you start thinking about adic spaces, you can have an affinoid adic space which is sort of locally of this form, but globally is only of this form. So if you read my Arizona lecture notes, I work at this level of generality, but for the purposes of today's lectures, all the examples that will come up in the other series will have this property. Because, for example, if you have a Banach algebra over a non-Archimedean field, then it inherits a pseudo-uniformizer from the field. So, no, it is true that if you have something analytic, then locally it is Tate. But it isn't true that something analytic is itself Tate. That's the difference. So yeah, from the point of view of the theory of perfectoid spaces, since you can work locally in many cases, you can just consider Tate things. And again, if you think about, for example, things that are QP algebras, those are automatically Tate. So you don't have to worry about this. Okay, so that was, so more, I want to, of course, the Tate condition is going to come up, but I also want to remind you that everything is going to be complete from the beginning. So I'm not going to say that my Huber rings are complete. Okay, so now let me give the definition of a perfectoid ring that I'm going to use, and this definition was introduced by Fontaine in his Bourbaki seminar on Scholze's original paper. It's more general than Scholze's original definition, and it's also more general than the original definition that Liu and I used. So I'll say a Huber ring is perfectoid if it satisfies the following two conditions. First, A is uniform. This is a condition that we saw in, I think, yesterday's lecture on adic spaces. So a Huber ring is uniform. This means that, so A upper circle, which is the subring of power-bounded elements, power-bounded, right? An element is power-bounded if its sequence of powers is it forms a bounded set. And the power-bounded elements form a subring, and we want this to be an ideal of a ring of definition. Or equivalently, it's enough to say that it's bounded, and then it's automatically a ring of definition. It's equivalent. So, for example, if A is a Banach ring, so a Banach ring which is Tate will always be a Huber ring, and the norm, there's some norm on it with a norm, so this norm doesn't have to be multiplicative for what I'm about to say, but I want it to at least be what's called power multiplicative. That means that the norm of x to the n is the norm of x. The norm of x to the n is equal to the norm of x to the n for all x and n. Of course, you could just write 2 here or p here, if any single value of n greater than 1 would suffice, 1. Then A is uniform. So in some of the examples, we'll see it's easy to see that there's a norm that has this property. Because, for example, if you actually have a multiplicative norm, that would do it. But sometimes this condition is quite tricky to check. It, of course, implies that A is reduced, but not conversely. So perfectoid is going to require uniform, and then the other condition, which is the analog of the main condition in a perfectoid field, is so there exists a Cedo uniformizer var pi. So I'm going to assume that p is divisible by the p's power of this thing, and such that, so that makes the following thing make sense. So if I take the power bounded elements, if I reduce mod var pi, then I have a well-defined Frobenius map that goes from the reduction mod pi to the reduction mod var pi to the p. Right? The point being that this ideal contains, these ideals contain p, so I do have a ring homomorphism, and again, I want this to be surjective. So in particular, if the Frobenius on the reduction mod p is surjective, that would imply this, but I've hidden in here an extra condition that makes this compatible with perfectoid fields. So note, a perfectoid field is a perfectoid ring. Otherwise, this would be a very bad definition. If I take if A is a field, so first of all, it has a norm that satisfies this property. So if it's a perfectoid field, it has a multiplicative norm on it. So that implies uniform. The absolute value is not, the value group is not discrete, so I can find a var pi like this, right? This is somehow saying, this is somehow saying that the value group is not, for example, just generated by the norm of p. So I can pick something of sort of small, whose absolute value is slightly less than 1, and use that as my var pi, and then the usual Frobenius surjective mod p condition will give me this. So this sort of packs together the various conditions in the definition of a perfectoid field. And so you can unpack this. So a perfectoid field is a perfectoid ring. So conversely, it's not hard to check that a non-Archimedean field, which is a perfectoid ring under this definition, is a perfectoid field. So if you have a non-Archimedean field, then these conditions are just a repackaging of the original conditions. Yes, in this case, A naught, yeah, if you start with, if A is a non-Archimedean field, then A naught is the valuation ring. Yeah, yes. If you have a non-Archimedean field, then its power-bounded elements are just the valuation ring. Well, writing harder is confusing because that's a person who's going to come up later in the series. More difficult, I'm going to talk about harder Narasimha polygon, so I don't want to confuse with a reference to him. So a more difficult statement, which is true, is that a field which is a perfectoid ring is a perfectoid field. So this is not obvious. If I have a perfectoid ring and it just happens that the underlying ring is algebraically a field, that does not a priori imply that the topology is given by some multiplicative norm. Right? So the main point of writing this down is to point out that on one hand, this is not obvious, but it does happen to be true by a kind of tricky argument that I wrote down. Like, the references in the notes. But
you have a field with a discrete valuation, then you can also automatically have a valuation field, right? So
yes.
Is there a way to manufacture perfectoid rings if you have a perfectoid
ring? There are examples. So I'm not sure what you mean exactly. So I don't think this is the answer to your question, but this is an example of a construction. If K is a perfectoid field, then there are various ways to manufacture examples of perfectoid rings, like the analog of the Tate algebra construction, right? So you can, of course, the Tate algebra over K will not be a perfectoid ring. But if you but instead of completing the ordinary polynomial ring for the Gauss norm, if you take the, so to speak, perfect polynomial ring, where you have T and all of its P power roots, if you complete that thing for the Gauss norm, so, right, literally this is OK adjoin T P to the minus infinity, complete for the p-adic topology, and then tensor over OK with K. This thing is a perfectoid ring. So that's an example of starting with a perfectoid field, you can make something that's not a field. And in fact, if you start with any perfectoid ring, this spits out another perfectoid ring. But having said that, I'm not sure I've answered your question. This is just an example. But yeah, and of course you can also do this with with T plus or minus. You can take Laurent polynomials instead, and that would give you also K angle T plus or minus P to the minus infinity. That would be the same thing, but with T inverted. That also gives you perfectoid ring. And in K, you can replace K with some perfectoid ring, get another perfectoid ring out. So this is, yeah. What's not so obvious is what sort of free property does this thing have, right? Right, polynomial rings are free objects in some sense. I'll let you think about what the corresponding universal property is of this thing. But. The hard part of this statement is that if you start with a perfectoid ring, so you start with a Huber ring, which is perfectoid, and you know that that every non-zero element is a unit, that doesn't immediately imply that the topology on A comes from some multiplicative norm. You can write down a power multiplicative norm, but a priori it won't be a multiplicative norm. So there's actually some intricate argument that's required to show that there is a multiplicative norm. I don't know an easy proof of this. Okay, so now we've seen some non-trivial examples. Good. Yeah, so just as an aside, I'll mention in Scholze's original paper on perfectoid spaces, he only considers algebras over a perfectoid field, in which case you don't really need to mess with the pseudo-uniformizer because you get it from the base field. You can just say the Frobenius mod P is surjective. And in my original paper with Liu, we only consider QP algebras. So again, where automatically everything is Tate, but we do have to have some analog of this condition. Which one? In this situation, or which? So when we're talking about a perfectoid ring, the A0, yes. What about the A?
That will have a multiplicative from the i-adic.
No, it's not. It won't be multiplicative. That's the problem, right? The norm of the product could be strictly less than the product of the norms. That's what I'm trying to avoid. Right. So in order to right, when you complete a field, when you talk about completing fields to get the real numbers and the complex numbers and the p-adic numbers, you always assume the absolute value is multiplicative, and that guarantees that when you complete the field, the completion is again a field. But non-multiplicative norms don't have that property. You can start with a field, complete it, and get something which is not a field. So that's why a non-Archimedean field really has to be topologized by a multiplicative norm, and that condition is hard to check in this case, but it turns out to be true. Okay, so let's talk about tilting. So I'm going to write down a proposition that looks exactly like the one that we had before. The proof is not exactly the same, but it's quite similar. So I won't say too much about it. Oh, and I should say I'll say a perfectoid ring, a perfectoid pair is just a Huber pair where the first member is perfectoid. So I'll say A plus is perfectoid if A is, by definition. This is maybe not the, right, this is maybe not quite the right way to write the definition. What you really would like is, what you should really do is say that a Huber pair is perfectoid if these conditions apply with A circle replaced by A plus. But it turns out that's actually equivalent. This implies the corresponding conditions with A circle replaced by A plus. So if A is perfectoid, then for any choice of the plus, A plus mod var pi to A plus mod var pi to the p will be surjected. So somehow the point is that the difference between A plus and any other the difference between A circle and any other choice of A plus is quite small, right? All of the 8 possible choices for A plus have to be contained in here, because they can only contain power-bounded elements. And the difference between A plus and A circle is quite small. So comment, A circle contains A plus, and the quotient is what's called an almost zero A plus module. i.e. it's killed by any topologically nilpotent element. So there's a notion of, in this study of perfectoid rings, one very often uses this concept of an A plus module being almost zero in this sense, that it's maybe not literally zero, but it's killed by anything which is topologically nilpotent. So for example, if you're working over a perfectoid field, you could say, well, for something to be almost zero, it has to be killed by all of the pseudo-uniformizers in the base field. So this is somehow saying that once you choose A, you don't have that much choice left for A plus because of the uniform condition. But anyway, so the point is that no matter how you formulate the definition of a perfectoid pair, it only depends on the underlying ring. It doesn't depend on which plus you use. So the tilting property can be formulated like this. So if I start with a perfectoid pair, then the natural map of monoids under multiplication from the limit of A plus to the limit of A plus modulo, there's a P in my notes which should be a var pi, so let me do it right here. It should say, this should be the var pi from the definition. This map is an isomorphism. So that gives this multiplicative monoid a ring structure, just like before. So I'll now write A flat plus to mean this common value. Yeah, maybe I can say it this way. The resulting ring, A flat plus, occurs in a perfectoid pair, A flat, comma, A flat plus of characteristic P, and it's this the kind of the completion. Well, completion is the wrong word. The thing that you get by filling, right? You get this thing by basically inverting some uniformizer on this. So this A flat is somehow determined by A flat plus. So note And moreover, I can write A flat as a monoid, as a multiplicative monoid. A flat is isomorphic to the inverse limit of A under the p-power map. And so the inclusion from here to here is the obvious one. As a the resulting ring. Right, so in the previous isomorphism, the thing on the left is only a monoid, but the thing on the right is a ring. So I'm going to use the fact that that's an isomorphism to transfer the ring structure to the left, just like I did before. And so I'm going to refer to this thing as a ring. It just has an exotic addition law. And that ring is called A flat plus. And it is the plus, I claim it's the plus of some, it is a ring of integral elements for some Huber ring of characteristic P, which I call A flat. And A flat, the underlying multiplicative monoid of A flat, is naturally this. So this can again be upgraded to a ring of characteristic P, which I call A flat, which has this A flat plus as a ring of integral elements. Yes, that occurs uniquely up to unique whatever. In characteristic P, the second condition is just being perfect. Yes, just as it was for fields.
So is this just saying that do this okay? You think that perfect dot X.
Well, I mean, it's including the fact that there is something to go to. I mean, this is not a definition. This is a lemma that there is such an object that, this is an isomorphism, and that you can upgrade this. That this thing, the ring structure on here extends to a ring structure on here, and so on. But yeah. Yes. No, this is a lemma. This is a lemma definition. So you have to check some things, just like you did in the field case. So, the proof of this is very similar to the field case. Again, it just uses the fact that this ultimately comes down to the fact that when you have a congruence between two things and you raise everything to the pth power, then you get to add a factor of p to the congruence. That's what is being used here. And that's true, that doesn't depend on fields. Okay, so again, I have a sharp map. So let sharp from A flat to A be the final projection. Right, so if A flat can be identified as this inverse limit, then there's a final projection, which is a multiplicative map, but not a ring map, because this is characteristic 0, this is not, this is characteristic P, this might not be. So I need to say that there exists a pseudo-uniformizer var pi bar in A flat such that sharp of var pi bar over var pi is a unit in A circle, or even A plus. So this is the analog of comparing value groups. I just need to know that my pseudo-uniformizer, right, my pseudo-uniformizer might not itself come from the sharp map, but there is something that sort of simulates it well that comes from the sharp map. And then once I've made that choice for such var pi bar, we have A plus modulo var pi is isomorphic to A flat plus modulo var pi bar. So once I synchronize things like this, then I have a theorem that says that the truncation, there's a truncation of A plus, which is isomorphic to a truncation on the flat side. And that again just comes from here. So there is a tilting operation which behaves very similarly to the way it did over for fields. while I'm erasing this, if there are questions, maybe it's a good time to ask. So this, I should say that the fact that you can tilt for things that are not fields, that's not a particularly new observation. So I told you that this notion of tilting for fields goes back to Fontaine. The notion of tilting things that are not fields already shows up in Falting's work basic work on p-adic Hodge theory. So the idea of extending some of this formalism past the category of fields is already due to Falting's, even if he didn't have the setup to do it at this level of generality. But yeah, so was there a question? No. Where? Here or? No, because this is in characteristic P, right? The condition is that the sharp of this thing in characteristic P is associated to my original thing in A+. So that's like it saying that it has the same valuation. And so now I can use that to say that the reduction of this possibly characteristic zero ring, modulo this thing, matches this thing which happens entirely in characteristic P. Yes, so sharp in particular sends A flat plus to A plus. But that's just the restriction of the map that it sends from A flat to A. Yes, but we already knew that because we already assumed from the outset that P is a multiple of this. Yeah, there are a couple of questions in the back.
Say only the result. You can take for 5 bar.
Yes. So retroactively, once you know this, then this is telling you that your original choice of pi bar could have been chosen to have a consistent set of p power roots and therefore to come from the image of the sharp map. It's just that in the definition you don't assume that, and in practice, when you write one of these things down, it's not actually obvious. It's not always obvious how to write down such a var pi, but it always exists. Yes, it's induced by sharp. Yeah, so it's induced by sharp, but it restricts to a ring isomorphism after you do this truncation. Okay, great. So that's the definition of tilting. And now I claim tilting has many similar properties as it did before. So for example, I can there's a theta map. So if AA plus is let AA plus be a perfectoid pair, then as before, and again, I'm not going to give the details, but it works similarly to the field case, there is a unique homomorphism called theta from Witt vectors of A flat plus to A plus, whose restriction, well, such that theta composed with the Teichmuller lifting map is the sharp map. So again, the sharp map from A flat plus to A plus extends to a ring homomorphism from W of A flat plus to A plus. It is surjective. That is, again, easy to see once you know the map exists. The hard part is to check that, again, uniqueness and surjectivity are both clear. The non-trivial part is to check that the Witt vector arithmetic is compatible with the relationship with the thing and the thing at tilt, but it's just as it was for fields. You might as well prove them together, actually. And the kernel is, again, principal generated by the analog of a primitive element, but I have to tell you what that is in this context. So what do I mean by a primitive element? So we'll say Z is primitive. Well, let me write that separately. Right, so what did primitive mean in the case of a field? Well, in that case, the A plus was a valuation ring, and the zero coordinate was something that was in the maximal ideal, and the one coordinate was a unit. So what is the right analog of that here? So let's say Z, which I write in terms of coordinates, if it's in A flat plus, is primitive if Z naught bar is topologically nilpotent and Z1 bar is a unit in A flat plus. Sorry, this is not legible. Let me just write it out. It says it should be say. So the reduction should be, i.e., so the reduction mod P should be topologically nilpotent, and then you have a second condition, which is equivalent to if you define the P associated P derivation for Frobenius, this should be a unit in this ring, which is to say its reduction mod P should be a unit. So it's basically the same condition as before. It's just I have to tell you what the condition is on Z naught, but of course this is consistent with the field case. Because having norm less than 1 is the same thing as being topologically nilpotent when you're in a field. I'm sorry? Yes, unit, sorry, unit. Thank you. So yeah, so you have a theta map, and you have a kernel of it, which is primitive, and you can guess what happens next. What happens next is that this makes sense whenever you have, so if I start with RR plus a perfectoid pair and characteristic P, then of course every time I identify it with the tilt of some perfectoid pair, I get a primitive ideal, and then the statement here is that the converse is true, is that primitive ideals give rise to untilts. So every primitive ideal arises as kernel of theta for some unique up to unique isomorphism, perfectoid pair A plus and an identification. So the data consists of a perfectoid pair and an identification of its tilt with the thing that I started with. So primitive ideals in Witt vectors of, so for every primitive ideal, I should say, in Witt vectors of R plus, so the primitive ideals in Witt vectors of R plus corresponds to isomorphism classes of untilts of the pair. Yes?
So far, most of what you're doing is at the level of the subject outputs.
Yeah,
All the definitions, constructions.
yeah, everything somehow involves the R plus, yes.
What is the information that's there in R which is not in R?
There isn't really, I mean, there isn't really any extra information. Well, yeah, you can recover R from R plus if you specify that, I mean, R plus comes with a topology, which you have to specify. It's not an intrinsic of the underlying ring. So, actually, no, I don't think that's, you can, yeah, if you remember the topology on R plus, then I think you can recover R. But you have to remember its topology. Somehow it doesn't, the same R plus can occur with different topologies on it. In this example, it's just the corresponding thing for the tilt. So this construction commutes with tilting. Thank you. I was going to make that remark. So the construction of Tate algebras commutes with tilting. That's it. That's a fun exercise. Where here? No. I did start with for the fields. The thing when I untilt some, I mean the tilt is always of characteristic P. So So when you untilt, you have to start with something of characteristic P, and then you realize it as the tilt of something, and then you get and then you match up the theta, the kernel of theta. Yeah. So R plus so it's R. You start with something of characteristic P. How can it occur as a tilt? Well, the ways it can occur are parameterized by the primitive ideals in WR plus. Yes, so in this example, if I start with, like in this example, the plus here, you could take it to be the OK angle brackets and so on. But if you start with a perfectoid pair, then you can make a plus ring where you put the plus ring here and then take power series with coefficients in the plus ring. I mean, the tilt of A does not depend on A plus. So that I wrote that in here. The tilt of A only depends on A. So, right, the plus is there in the Huber space theory, right? The plus kind of affects something about the boundaries. And so a lot of the basic constructions don't depend on the plus until you start making spaces. And then the plus matters because it tells you whether certain things are coverings or not. But in the algebraic theory, things don't tend to depend too much on the plus. Okay. Right, so some compatibilities with tilting. So there's an analog of the compatibility. So, right, of course, you can untilt, if you have a ring and it's tilt, you can make extensions of the tilt and then bring them back by using, right, so if A plus has tilt, A flat plus, and if I have a morphism from this thing to SS plus, then I can come back and get like a BB plus, right? Because this tilt comes with the extra information of a primitive ideal. I can extend that primitive ideal to the Witt vectors of S plus and then untilt, and that gives me that would give me this, i.e. the categories of perfectoid pairs over, AA plus and over A flat plus are equivalent. So, right, a priori, if you start with this thing in characteristic P, you don't have a canonical untilt. But if there's a base ring, which is perfectoid, if you start with a perfectoid base ring and it's tilt, then you have an ideal that untilts this thing back to here, and you can just extend that ideal to any algebra over this. So from this property, you know that any perfectoid algebra over this thing has a distinguished untilt, which is a perfectoid over this thing. This is any map of perfectoid pairs. Yeah. You can always lift it to something. Yeah. There's a question, of course, of what properties are preserved by the lift, which I'll give you one or two examples, but they're more in the notes. This BP plus is unique up to unique isomorphism. Yes. So this is really an equivalence. Yeah. So what properties? So you can then ask, well, what properties are preserved by this correspondence? Yes. This one is in characteristic P.
I know. You're starting with
You start with, say, characteristic 0 if you want.
then you print it.
Yes.
And then you have a map of perfectoids in that.
Right. So, yeah. So you have this. So say you take this map here. So obviously, if I'd started with this map, I could tilt it. But what I'm saying is, if I start with this map, then I can use the extension of this ideal to untilt this pair. And so I get functors both ways. No, not yet. It's arbitrary. But you can ask, well, if you can ask about what properties are preserved when I do this. I mean,
I take SS plus until it to BB plus.
yes,
That's a perfectoid pair.
yes.
And then I tilt it again.
Yeah, then, I mean, there's a natural isomorphism between the composition and the identity. I mean, you know, they're functors. I can't tell you, I can't say that it's on the nose, that, but it's canonically isomorphic when you untilt and then retilt. Okay, so what properties are preserved? So somebody asked about finite. Well, let me not try to say anything about finite. That gets a little bit complicated. Let me say finite et al. So if I have a there are two statements hidden in here. One of them is easier than the other. So one is that if I start with a finite et al. Thing here, then the untilt will be a finite et al. Morphism. That just means that B is finite et al. Over A, and B plus is the integral closure of A plus. But I mean more than that. I also mean that if, so this includes a much stronger statement, which is the analog of the compatibility of tilting with finite extensions of the field case. If A to A plus to BB plus is finite et al., and AA plus is perfectoid, then so is BB plus. That's the analog of the very strong statement about fields, which was somehow the main theorem that I stated in the first lecture. So this is in fact quite a deep statement. The fact that when you start with something perfectoid and you go finite et al. Above that, you stay perfectoid. That's again not obvious from definitions, and this is again sort of in the various papers, the various references, this sort of one of the foundational things, both in my work with Liu and in Scholze's work. One of the key points was to deduce this. I won't say anything right now about how to prove this. Maybe at the end I can say a word or two about this, because you don't do this first. You do some other stuff first. Okay, other properties that are preserved. Yes, in the sense that if this statement would not be true without et al. You can have a finite extension of something perfectoid which is not even uniform, because you can just add a nilpotent, for example. So, yeah, so I need something et al. I can get a little bit less, but not too much. Yes? Oh, finite et al. Means that A to B is finite et al., just as a map of rings, and B plus is the integral closure of A plus under the map from A to B. So that's what finite et al. Means. B plus is not in general going to be et al. Over A plus. It has a certain property called almost finite et al., which I won't try to say what it is, but is an important. That's an important refinement of this statement. That's essentially what's called the almost purity theorem. It's a generalization of Folting's original almost purity theorem. So yeah, but A plus to B plus is not literally finite et al. It's only almost. Okay, some other algebraic properties that are preserved. Injectivity and surjectivity. I won't say too much about those, but so it means that sort of the notion of a closed immersion can be tilted in some sense. But this doesn't have this stronger property. This is in the weak sense. So meaning it doesn't include this parenthetical. So you can have a perfectoid out in characteristic 0 and take a quotient of it which is not perfectoid, because, for example, it's not reduced. Right, like my perfectoid Tate algebra, if I divide by t, I get some horrible non-reduced ring, because I still have all these fractional powers. So it's just that if you have something injective or surjective here, you can lift it to get something injective, surjective here, and if you start with a map of perfectoids that's injective or surjective, then you get that other person. So here's the one that's actually important. The property of being a rational localization. So when I say a rational localization, I mean one of the localization maps that appears in the construction of adic spaces, right? If you have the adic spectrum of a ring, then it has all these rational subspaces that we defined yesterday afternoon, and they have, right, the sections of the structure presheaf and the plus structure presheaf give me a pair, And so there's a restriction map from this pair to the new pair, and those maps are what I call rational localizations. So i.e. it's like A plus to O of U, O plus of U, where U is some rational subspace. So the rational localization map, the property of being a rational localization map is preserved by tilting, and this is again the strong sense. Any rational localization of a perfectoid is again a perfectoid, and there's a one-to-one correspondent, and there's an equivalence given by tilting. If you have a finite map of perfectoid fields, okay, obviously it's étale because it's a map of fields. You mean on the valuation rings? The map of valuations rings will be almost finite étale in some sense, which I won't define. Generically. I mean, a morphism between fields is automatic, I mean, is... Yes. 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 Yeah, you can say that it becomes étale after inverting some discriminant in a not canonical way, but yeah, this comes up in like if you look at applications in commutative algebra, like the direct sum and conjecture, you use this property a lot that a finite morphism becomes finite étale when you after inverting something that looks like a discriminant. Yeah, so this is what it's saying. If you have a map between perfectoids, then you can, but you need to know that both sides are perfectoid. Then you can check these properties on the tilt. But it doesn't, right, it's not the case that automatically a surjective map, I mean, it's obviously for injectivity, it couldn't possibly be the case, but even for surjectivity, just because you take a quotient of something perfectoid doesn't mean you're perfectoid, because you might not be reduced. Yeah, the strong sense means a localization of a perfectoid is perfectoid, which is important because this means that a localization of a perfectoid is uniform. And as this came up yesterday afternoon, this has an important consequence that well, you have to define what you mean by an étale morphism of a perfectoid pair, which I wasn't going to try to do right now. Because you don't want it to be algebraically étale, because then you won't get a Huber pair. You could say something like, well, take the completion of an algebraic étale morphism, but that's not really intrinsic. Well, yeah, here I'm just taking rational subspaces. You could say more, but time is short, and this is going to be sufficient for our discussion. So this implies that a rational localization of a perfectoid is always uniform, and therefore, the theorem, right? There was a theorem that came up last time that if you have something where all the localizations are uniform, then the structure pre-sheaf is a sheaf. So this was proved by two groups independently, Buzzard, Verbergus, and Vihara. So the references are in the notes. This implies that A is what's called sheafy. Maybe it's better to say A plus is sheafy, but really it only depends on A. The structure pre-sheaf on SPA of A plus is a sheaf. I should also mention, this is a result of mine with you, that moreover, it is, well, yeah, so it turns out whenever the structure pre-sheaf is on an adic spectrum is a sheaf, then it's actually acyclic. The higher cohomology groups vanish. So it's like the Tate theorem is back. So you have something like the Tate acyclicity theorem, and so this means you can now define a perfectoid space as an adic space locally, well, or a locally V-ringed space, locally of the form SPA AA plus, where AA plus is perfectoid. So perfectoid, right, so this definition doesn't really make sense until you know that perfectoid rings have the sheafy property, that they give rise to structure presheaves, which are actually sheaves. Because then, now you can make genuine adic spaces by gluing together the adic spectra of perfectoid rings.
Also, like Chekhov expression of coverage.
That's because of this, absolutely, which is crucial for applications like thinking about the perfectoid Chamorro varieties or something, where you want to compute cohomology. Yeah, so so perfectoid opens give you acyclic things that you can use in a check resolution. That's right. That's why this is important. Right. So, for example, I won't write this on the board, but you can, since you know what the analog of a polynomial ring is. I gave you this Tate algebra construction. You can define analogs of projective space by gluing together n+1 disks, polydisks, or you can also do things. You can also make analogs of toric varieties in a similar way. And these examples already appear in Scholze's original paper because the intended application there was studying cases of the weight monodromy conjecture for hypersurfaces in a projective space. And so he uses the analog of perfectoid projective space, or the perfectoid analog of projective space. So he uses that construction. And basically everything he does in that paper could also be done for toric varieties, because basically the point being that the construction of a perfectoid projective space, again, commutes with tilting. So if you built the analog of Pn over some perfectoid base field, or perfectoid base ring even, then tilting that commutes with, making that construction commutes with tilting. So the perfectoid over, the perfectoid Pn over K tilts to the perfectoid Pn over K tilt. This kind of thing. Let's see. I think somewhat miraculously, that is all that I wanted to fit in. So let me stop here and take some more questions if we have them. Right, so a toric variety is defined by some combinatorial data, a fan or something. And so the point is that, right, how do you build a toric variety out of this combinatorial data? Well, you have these charts which are, affine spaces with some of the variables localized. You can directly translate those into corresponding Tate algebras with some of the variables inverted, and then glue, by making some identifications of monomials. And then when you do that, you get some kind of perfectoid toric variety. So the recipe kind of works similarly, and you can also compute the cohomology of bundles on those things. Yes? Oh, you're asking about fiber products?
Yeah.
Yeah, sorry, that was the one other thing I should have said. Yes. So if you can define a completed tensor product of two Huber rings over a third Huber ring, and when all of them are and likewise for pairs. So when you do this, there is an operation of completed tensor product for two perfectoid pairs over a third one that does exist. It's again perfectoid, and using that you get fiber products in the category of perfectoid spaces. Yeah, which is an important point because the category of adic spaces does not a priori have fiber products because the sheafy property does not necessarily behave well under these completed tensor products. But perfectoid spaces, yeah, one of the beautiful things about this theory is that, yeah, you have fiber products in this. So a lot of things work very nicely that don't work very well in the larger category of adic spaces. Yes?
when you defined the perfectoid pairs, you said that you can take A0 to be A plus, or
Yeah, that would be one way to extend A to a Huber pair is to take A0, yes.
So you just mean take the natural map of A plus and A0, then there's some sort of preservation of property, or I mean.
Yeah, so what I was saying in that case is, right, so when I defined a perfectoid ring A, I had this property that A0 modulo pi, the Frobenius on that is surjective. So the lemma that I didn't write on the board is that if A plus is a Huber pair and A is perfectoid, then if you take A plus mod var pi, the Frobenius on that is again surjective. So there's two equivalent ways. You could have either defined a perfectoid ring, just in terms of the circle, and then say that any extension of it to a pair is considered perfectoid, but it's better to actually prove that that implies a corresponding property directly formulated in terms of the pair. So there's just some lemma that I didn't write down that equates those two. So is regularity preserved under tilting? Well, I don't know how to formulate regularity because we're not talking about Noetherian rings, right? A perfectoid ring is almost, the only way a perfectoid ring can be Noetherian is if it's a finite product of perfectoid fields. And regularity is a property that is a Noetherian property. So there is a way to talk about regularity in this context. There's a notion of semi-regularity that comes up in like the Pottmore-Scholze work and so on. So there is a way to define regularity, something like regularity in terms of truncations. So you can work with that, but you can't literally formulate the condition that A is regular because that you don't have a Noetherian property except in trivial cases.